Okay, hi everyone. Could we please request you to get settled? I want to welcome all of you to the second installment of the MS Vardya lecture series, where we invite distinguished astrophysicists from around the world to come and teach us about the most exciting frontiers of astronomy and astrophysics. And so this year we have with us Professor Sarbani Basu, who is a distinguished professor at Yale University. I'll tell you, of course, about her in a little bit. But before I do so, could I please request all of you to put your cell phones on either silent or vibrate mode or something so that we don't disturb this lecture. And let me just take this opportunity to also request Professor Bhashwati Mukherjee, who's the chairman of our department, the Department of Astronomy and Astrophysics, to come and speak about TIFR, the lecture series, Professor Vardya, and just tell us, set the stage, so to speak.
Good evening, everyone. Mr. Sarbani Basu, our speaker this evening, Ms. Rekha Koita, Mr. Rizwan Koita, colleagues, students, members of the audience. On behalf of the Department of Astronomy and Astrophysics at TIFR, it's my pleasure and privilege to welcome you to the second MS Vardya Memorial Public Lecture. I'll tell you a little bit about TIFR because this is a public lecture. Research at TIFR at Colaba and all its centers across the country covers a large gamut of topics in physics, chemistry, biology, mathematics, and computer science. Details of our science activities are available on our website, so I will not go into those. However, at TIFR, we not only work on cutting-edge science, but it is also our mission to engage with the public at large and convey to them the excitement of our research through active outreach programs. The outreach activities at TIFR were formalized for the first time through Chai and White program that we organize every alternate Sundays in Prithvi Theatre and Ruparel College. This program has been successfully running for the last 16 years, and many of you may have attended many of the sessions. And it has actually spawned similar programs in other TIFR centers. And organizing public lectures such as these, where exponents in different disciplines speak about the excitements in their fields, has also been our long tradition in public outreach. Today's lecture is a part of a series instituted in the fond memory of Professor MS Vardya, who together with Professor S.M. Chitre established the Theoretical Astrophysics Group in TIFR in 1963. We are deeply grateful to Mrs. Rekha Koita, daughter of Professor Vardya, for this generous donation which has made the lecture series possible, and also to Professor Sarbani Basu, an eminent astrophysicist, for accepting our invitation to deliver this lecture. I'll tell a little bit about Professor Vardya. Born in 1933, Professor Vardya did his MSc from Banaras Hindu University and PhD from Yale University, working on envelopes and interiors of late-type stars. The main emphasis of his thesis was to compute hydrogen-helium adiabats, incorporating the physics of molecular hydrogen to provide better boundary conditions to radiative cores in late-type stars. He subsequently was a postdoc in Berkeley before he joined TIFR as a faculty member. His research work here primarily involved development of model stellar atmospheres for late-type stars, including opacity effects arising due to the presence of molecules and molecular ions. And later, he also looked into data from observations. He was a pioneering molecular astrophysicist whose work probably has become more relevant in the later years when observations of molecules in astrophysical environments became possible with improved technology. Professor Vardya, together with his student, also later a faculty member in TIFR, Professor S.P. Tarafdar, had organized one of the first conferences in astrochemistry. It was an IAU symposium. IAU is International Astronomical Union Symposium number 120, which was held in Goa in 1985. And why I'm quoting, I'm mentioning the summary of the proceedings because it was kind of unique at that time. It said that the symposium covered all aspects of astrochemistry, from the early universe to comets and meteorites, except ionospheres and planetary atmospheres. Basic atomic and molecular physics, experimental and observational results, and theoretical calculations and modeling all were stressed. In the era where we heard the term interdisciplinary, this is probably like it never said it was interdisciplinary, but this is as interdisciplinary as it can get. So, and Professor Vadia, beyond this, was also actually, he served, had a long stint as the editor of the Bulletin of the Astronomical Society of India during 1966 to 1973. Most of us have not like walked with him or seen him, but it so happens that our first speaker of this series actually knew him, Professor Evina Van Dishoek. She knew him, and also our speaker this year, she's an alumna of TIFR. She did her PhD from here. She also was in the same theoretical astrophysics group where when Professor Vardia was here. So we considered this to be, we ourselves to be extremely lucky to have been able to invite Professor Basu, who knew Professor Vardia personally. Once again, I cordially welcome you all to this lecture and thank you all for being here.
Thank you for that introduction, Ashwati. So I will take a few minutes to introduce our speaker to you before but before I do so, I would like to invite our very generous donor, Ms. Rekha Koita, who is the daughter of Professor Bhartia, to say a few words about her sense for this and what she, why she made this donation and how she thinks about this. Ms. Koita.
Hello, everyone. Thank you, Shravan, and thank you, Bhaswati, Arnab, and all those who have helped to put this together. And a big, welcome and thank you to all of you who are here today. I've grown up at, TIFR in the kind of very privileged, I think I'm very privileged to, grow up here in the TIFR colony, and coming here was, a very regular affair for us. So this is a place which has a lot of, fond memories, and I feel extremely nostalgic every time I come here. I had been wanting to do something, in my father's memory. And he was always very passionate about astronomy, astrophysics, and, setting up this department along with Professor Chitre here at TIFR was something that, it was one of his dreams and something that he was, so totally kind of his whole life revolved around TIFR and the department here. So it felt only fit to do something at TIFR, and being here and a person, a topic like astronomy has also a lot of public appeal, and I thought that in the spirit of also publicizing and popularizing science and popularizing astronomy, to have a lecture series in his name, I thought would be a very fitting tribute to him and something that he would, wherever he is, I think it's something that he is probably happy about. So really big thank you to the entire team at TIFR, my friend Arnab and Bhaswati, Shravan, everybody else. And let me just, not kind of take any more time, but I think we're all waiting to hear from Professor Basu. And thank you so much, Professor Basu, for taking out the time to do this lecture. It really means a lot to me. I think especially the fact that you were here and you were doing your PhD while my father was still at TIFR, so you have met him, interacted with him. You also, coincidentally, Professor Basu is teaching at Yale, and my father did his PhD from there, so that's kind of another connection. So there is some serendipity for sure. So thank you very much.
Thank you so much, Ms. Koita. So let me take 2 minutes to introduce our very eminent speaker for the day, Professor Sarbani Basu. Professor Basu is the William K. Landman Jr. Professor of Astronomy at Yale University. I first met her 21 years ago, 21 and a half years ago to this date. In fact, at Yale, where we had a series of conferences. So I've known her for a very long time. She's very kind. She's always been, she's been a mentor, and she's really done outstanding work over all these years, which I'll briefly describe to you before she begins explaining why this is such an exciting topic. Professor Basu worked, at least for a good fraction of her early career after she joined Yale, maybe even a few years before then, on the internal structure of the sun and understanding how and why it varies with this, with why magnetism varies, what's happening in the solar interior, and so on. A central theme to her work is understanding how the structure and rotation of the sun vary over what is known as the solar cycle, which she'll explain in short order, and how these processes operate in the larger galaxy and other stars. She was educated in India, as you've heard. She was an alumna of TIFR, and she got her PhD in 1993. And she subsequently was a postdoctoral scholar at the Queen Mary College in London. Subsequently at the University of Aarhus in Denmark. Then the Institute for Advanced Study at Princeton, and then finally as a professor at Yale in 2000, where she's been ever since. Now, I'll take a moment to describe what she did at Princeton. It's a very important series of papers that she wrote at the time. There's an outstanding problem called the neutrino problem, which was focused on understanding why we were only observing 1/3 of the the neutrino flux that we thought should be coming from the sun. And she made a series of very important contributions on this topic with her postdoc mentor at the time, Professor John Bacall, who's a Princeton professor. And during this time, she's really continued her collaboration also with TIFR, interestingly, with Professor Antia, who many of you may know. It's a multi-decade collaboration that she's maintained, where she's made a series of influential contributions in, as I said, understanding this interior of the sun, its dynamics, its magnetism, its rotation. Every year there'd be Basu and Antia and Basu. So it was so funny when I was really young and I would go to conferences, people would always know Sarbani Basu because she was, of course, well known everywhere internationally. But people would say, "Do you know Antia?" When I first joined TIFR and I'd go to conferences abroad, they say, "Do you know Antia?" "Oh, I've read this Antia and Basu, or Basu and Antia." So that's sort of this defining collaboration, almost a very influential collaboration in solar physics and in understanding the interior of the sun. So her work has, of course, been recognized by numerous awards. She won the Venu Bapu Gold Medal of the Indian Astronomical Society of India in just before 2000. She was awarded the George Ellery Hale Prize of Solar Physics of the American Astronomical Society in 2018. This is the highest prize in solar physics. It is a very impressive prize indeed. So the laureates are the laureates have unfailingly made very deep contributions to our understanding of the sun. She's a fellow of the American Association for the Advancement of Science, AAAS, and of the American Astronomical Society, AAS. So today, Professor Basu continues to shape the field through her research on solar cycle variability, analyzing data from a variety of space missions, understanding stars. She mentors students, postdocs, many of whom have gone on to become leaders in solar and stellar physics. And her work continues to remain central to the effort of connecting seismic measurements, which are the vibrations of the sun and stars, to our understanding of the physics of these bodies. So without further ado, I would like to introduce and request Professor Basu to.
Am I audible? Okay. So I would like to start by saying Thanks for inviting me here. It's lovely to be back in my academic home and see this lovely campus again. And I would like to thank Mrs. Koeta for this opportunity to give this talk, because as you yourself mentioned, I used to know Professor Verdia, who was a mentor when I was a PhD student, and as you said, was a Yale alum, which of course is fantastic. So these are two papers which are actually defining papers written by Professor Verdia, which, the reason I show them, they're very technical papers, is because you see Yale University Observatory, New Haven. Now, that's a connection. I actually had the privilege of looking from afar at a copy of his PhD thesis because it's a 1959 thesis, wasn't allowed to touch it. It's actually in the Rare Books Library. So I saw that. I was hoping I could get a picture of it to show, but I couldn't do that because of they were having some renovations, etc. So I'm sorry about that. But you can see these papers. Now, what I'm going to talk about is us and the sun. We actually live. I mean, we are taught that, oh, the space between the Earth and the sun, it's interstellar space, interplanetary space, actually. It's very thin, almost vacuum. Yes, it's almost vacuum, but it's not fully vacuum. It's filled with solar wind. The sun emits particles, and we live in the stream of those particles. So this is an artist's impression of what's known as the heliosphere, that is the sphere of influence of the Earth. It's a gigantic structure. So we are, let me see if this, yes, we are here. I'm sorry, this visual is not very good, but these are the orbits of the planets. Okay, so the sun is here, we are here. The reason we have this sort of a structure is because the sun is moving around the galaxy, and the material of the galaxy, again, is not vacuum. There are particles, we call it the interstellar medium, and when the solar wind interacts with the interstellar medium, we get the shocks. Those shocks don't affect us because we are sitting pretty here. Now, just a matter of interest, we have become a galaxy-faring civilization because our robots, Voyager 1 and Voyager 2, now are actually in the interstellar medium. So yay, us. Yes, we can't go there ourselves, but we have sent our proxies, which is almost as good. Now, if you want to know how far, so we are here, okay, we are going there, and how far is Voyager? There's a lovely NASA website which will tell you exactly how far Voyagers 1 and 2 are now. To get a scale of the helio, of the sun's influence, this distance, I made this slide about 3 weeks ago. At that time, it was 170 times the distance between the Earth and the sun. So in planetary astrophysics, particularly solar system physics, the Earth-Sun distance is the unit of distance. We call it 1 astronomical unit. This was already 170 astronomical units away, and it took about 45 years to reach that. So those of you who want to voyage to other planetary systems, other stars, just think of that. We do not have the technology yet. But of course, this is 1970s technology. Maybe we are a bit faster, but who knows? Okay. But before I talk about the influence of the sun and what's essentially known as space weather, which is the disturbances on the Earth's atmosphere, actually the Earth's magnetism by the sun, let's take a very quick look at the sun, what it does, what it can do. So, very quick look. The first thing, the sun is actually a normal, middle-aged, low-mass star. Okay, main sequence is the longest stage of a star's life. It's the time the star fuels itself by hydrogen fusion in the core. That's the most stable time. So, and we're lucky that we live around a low mass star, because high mass stars don't live very long. It's a reasonably placid star. In that sense, we are very, very lucky. Okay. It's a special star. Why? Because, hey, it gives us the energy we need, right? We exist because of sunlight, energy from the sun. So it provides almost all the energy that we use today. And I write almost because of the little fraction of nuclear energy that we use, the nuclear power plants. That's not solar. That's pre-solar. But everything else is either directly or indirectly sunlight. But the sun is also special because we can actually use it as a laboratory to study physics. I won't get into that today, but the sun being closed, we can actually get very good measurements, which allows us to test physics. Okay, so this is the sun in a nutshell. What happens? Why do we study it? Well, it affects everything. It's the main source of energy. It's responsible for life. Solar energy converted by plants into carbohydrates basically gives energy to every other life form on Earth. So without solar energy, well, I shouldn't say every other life form. I'm a scientist. I should be very precise. There are life forms on Earth that rely on volcanic energy deep inside the Earth. But think of most life. Solar energy. We depend on it directly, indirectly for solar, for energy. It affects climate. We live, I mean, this is Mumbai. Remember how hot it gets and humid it gets in the summer? Sun. However, the magnetic cycle of the sun can affect us. I'll talk about the magnetic cycle. And geomagnetic storms caused by magnetic activity of the sun can actually harm technology. It doesn't affect life directly. We did not know of these effects till the first technology was built. So only 1859, the first effects were felt, but it affects technology. So, well, naturally, that's why we care, right? It affects everything. And it's no surprise that people used to worship the sun. It's not just here among Hindus who had a sun god who still worship the sun, but also Egypt, where the sun god was one of the main gods. It made perfect sense. The sun is the life giver in that sense. Okay, now, but gods are not always benevolent. The sun ejects enormous amounts of energy and matter. And once these affect this Earth's magnetic field, they can cause geomagnetic storms, which can be a problem. Which is why in today's heavily technology-dominated society, a lot of effort is being put into understanding the effects of the sun on the geomagnetism, because this is what we call space weather. Everything, think of your grids, your electricity grid. Think of, communications. Everything is affected by Earth's magnetic field, and if there's a disturbance in the Earth's magnetic field, it's going to cause a problem. Okay. So this is a simple graph, courtesy of the US NOAA agency, which deals with atmospheric effects. They're also the main agency studying space weather, which sort of tells you what are the things that can happen if you have a bad geomagnetic storm. Electricity disruption, GPS signals can be off by kilometers. If you rely too much on GPS, you'll be in trouble. It can kill satellites if you have a big emission. In fact, early in 2024, there was a solar storm. SpaceX was warned not to launch satellites They launched 2,500 satellites. Most of them failed because of the solar storm. So we need to know. And of course, if there are astronauts in space, for example, at the International Space Station, they would get a very heavy dose of radiation. In fact, I remember once being on a flight from New York to Hong Kong, and it flies very close to the magnetic pole of the Earth. There was a huge solar storm, so the flight path was changed so that because, long-haul flights go well, 30,000 feet, so 15,000 meters. So to avoid giving passengers and crew a heavy dose of radiation, they had to change the flight path. So it is not, the effects can be real. The effects can be harmful, but you have to keep in mind it's because of technology. So don't think that how is it that we didn't know that the sun is affecting life? It's through technology. So let's get back to the sun again. This is an eclipse image, a solar eclipse. And we need this image because we don't actually see the outermost layers of the sun. The visible image of the sun that we see, the visible disk, is what is generally called the photosphere because most of the light that we get from sun comes from that layer. There's a very thin, very hot layer above that, which is called the corona or the crown. But it is so thin, the light is so dim that we don't normally see it. We need an eclipse. So this is an eclipse photograph where you can actually see the corona and you can see that it is not a sphere. Most of the emissions that occur, the mass ejections, occur from the corona. And one of the mysteries in solar physics is still, how is it that the visible layer is at about 5,000 degrees, while the corona is at about 1.5 million degrees? Where does the energy come from? How does the energy go up, change the temperature? It's one of the mysteries which people are trying very hard to solve. We know it has to do with the magnetic fields on the sun, but yeah, the exact mechanism is unknown. Now, the Earth does have a magnetic shield because it has a magnetic field. Now, if there were no solar wind, the magnetic field of the Earth would look like these white lines. It's like a perfect dipole, the magnets you play with at school. Okay, there's a North Pole and a South Pole and lovely symmetric lines. But what happens is the sun, the solar wind hits the Earth this way. And since the solar wind contains particles which has magnetic fields, it'll compress the magnetic field on the sunward side of the Earth and open up the magnetic fields on the tail side. So this is the normal configuration of the Earth's magnetic field. Now, what happens? So this is just another picture of the normal configuration. Okay? Now, what happens often is that you get a large burst of energy or particles from the sun. This particular, so when it's just energy, we call it a flare. When it is particles, we call it a coronal mass ejection. Flare is it's only light, but light has energy, so it can ionize things. Now, this is an image of the so-called Bastille Day flare because it happened on July 14th, which in France is celebrated as the Bastille Day because that's the day when the Bastille was attacked by the people. But what happened is this caused a huge geomagnetic storm and actually killed a few satellites. So by killed, I mean it damaged their electronics so much that they were unusable. Now, that was a flare. This, I'll show you an image, a movie, if it works. Come on. Oh, yeah. Oops. Yeah, come on. This, as you can see, things emitting from the sun, that's what's known as a coronal mass ejection. There, that's a big one. Now, if you're wondering what is going on in this image, we can't see the corona normally, as I said, and we need an eclipse. But in the late 1940s, people figured out how to make an eclipse artificially within a camera. Those cameras are known as coronagraphs. Now, the problem with the coronagraph is you have to block out more than just the sun's disk. So you see this white line here. Oh, these are cosmic rays hitting the detector because of the solar flares. This is actually the sun. In a total solar eclipse in this era, we are very lucky the moon, the relative sizes, the apparent size of the moon and the sun are exactly the same. So we can see things nicely. But in a camera, to avoid stray light, you have to cover twice the area. So that is why this looks like this. We have actually covered the sun, created an artificial eclipse, and then we can see things happening in the corona. This instrument is known as LASCO. It's on board a spacecraft called the Solar and Heliospheric Observatory, which is actually 3 times as far away from the Earth as the moon is. So it's never eclipsed. And the nice thing is it also gives us early warning of, a solar event, because it takes 8 minutes for light and many hours for particles to reach. But SOHO detects them, sends a signal to Earth and say, oh, be prepared. So it's one of our early warning systems right now. What happens? This is going to be an animation, if it gets working. Which will show first a coronal mass ejection, which will travel and hit the Earth there. And you can see how the Earth's magnetic field is disturbed because one of the layers from here got broken off and it formed a closed layer here. And the particles travel close to the poles and give these aurora. That's how you form an aurora, the powerful aurora, that is. This is just another version of that. Just wanted to show that to you again. Yeah, the animation isn't appearing very smoothly, but that's because I'm sharing this by Zoom, so yeah. Okay. And if you want to see them simultaneously, there you go, boom. Now, there are actually historical records of these super aurorae, if you wish. Actually, last year and even today, I live in Connecticut, which is at a latitude of 40 degrees south. And even there, we could see aurora. Normally, the aurora, they are confined to the polar regions. So places like Finland, Iceland, they get the aurora. But if you have a strong enough emission, you can see auroral emissions even at low magnetic latitudes. So this is a picture from a few months ago in the US, taken by a space physicist known as Robin Millen. She loved space photography, so she took that. But this is this year. This is a woodcut from, I think, 1600, a European woodcut, showing red skies. And it also shows sort of people wondering what these red skies are for, because you are not supposed to see aurorae in places like Italy or France. So what happened? And in fact, there are even older records. This is a clay tablet from the Mesopotamian civilization in cuneiform, which basically says on the night of the 29th, I don't know what the month, because the calendar was different, a red glow flared up in the west at Babylon. This happened in 500, now we know it's 12th to 13th March at 567 BCE. So, many years ago, but there are records of this. Of course, 2,500 years is nothing for the sun. The sun is 4.5 billion years old. Okay. From our point of view, it just seems very long. So these records have existed for a while. Now, Babylon was at 41 degrees magnetic latitude. And the reason it says magnetic latitude is because the magnetic pole of the Earth and the geographical pole of the Earth don't coincide. And aurora, etc., you have to measure from the magnetic latitude because it's the magnetic fields that matter. Mumbai is 13 or 14 degrees. 13 degrees south, okay? So this is a timeline, an interesting timeline, which shows both the evolution of technology and when we've seen these powerful emissions, where you could see these. So you can see there was one at 1730, but 1730, well, there was an association which tried to observe them, but there really was no technology to speak of, no electrical or electronic technology, okay? The first battery was 1800, so forget about it. Now, the first magnetometer, which measures magnetic fields, was 1833. Now, commercial telegraph, that was the one technological development which actually could be affected by storms. Why? Because telegraph has wires. If you have wires in a moving magnetic field, it'll induce extra electricity. We generate electricity by moving magnets, okay? So you have water for hydroelectric power, moving large magnets, that'll generate electricity. This is the opposite. The conductor is stable, but the magnetic field is changing, which is exactly the same thing happening. So you can affect telegraph wires. And I'll come to 1859 very soon. Because that was the first time we saw the effects of these solar flares. But there have been more. And yeah, Bombay, Mumbai, 13 degrees south, we're never going to see anything here. If you see aurora in Mumbai or anywhere in this latitude, we are all in deep trouble. So you should be lucky. You should feel lucky. So the first indication of the effect of, solar storms on society was what we call the Carrington event of 1859, named after Carrington, who actually observed the flare. He was an amateur solar physicist, and he observed the flare. What happened is, remember, telegraphs came a few years before this? Telegraph operators reported sparks. And in some cases, some found that it was impossible to transmit or receive dispatches because the atmosphere was so charged. In other places, there was so much electricity induced in the telegraph currents, they could detach the batteries and still send telegraphic messages. Okay. And these are only telegraphs, and think of the technology that we have today. And the worrying thing is, ice core samples have showed that the Carrington event was twice as big as any other substorm in the last 500 years. But records and statistical studies of other stars showed that Carrington event, yes, it was very powerful, but there could actually be even more powerful events. But that's the nature of living in the atmosphere of a star. So some other more recent effects, this was 1859. Think of 1989. There was such a large storm that you could see aurorae right up to southern United States and Mexico. The entire northern grid, electric grid of Canada tripped because there was so much induced current in the wires, it overloaded the transformers, and one of the transformers burned and tripped everything else. Okay. Now, The US fared better, but power grid problems erupted. Okay, didn't have a big blackout, but there were power grid problems. Interestingly, the space shuttle discovery found they were getting anomalous pressure readings, which disappeared the moment the effect of the sun went away. And there were satellites that had to be reacquired because they were losing communication. So it matters. And 89, there were fewer satellites than we have today. There were no communication satellites in 1989. However, the scariest thing is 1967. Okay, before that, so there was a report by the US National Academy of Sciences, who were charged to figure out what would be the damage caused by a Carrington Light event today. Trillions of dollars. The reason is transformers, you can't just go to a store and buy an electrical transformer. They're generally made to order. So if you don't have electricity, half your productivity, more than half your productivity is gone. So the total damage in economic terms could be immense. Think of the fact that you won't be able to use your cell phones. Can you imagine banking everything without your cell phones today? It's just unheard of that not being able to use your cell phones. You can't get an OTP because there's no cell phone. You actually have to go back to the bank and put an angutha chap and let them see whether they give you the money. No Paytm, no UPI. However, the ultimate societal impact was an almost World War III in 1967. There was a huge flare from the sun, which caused radars in Greenland and other the Arctic Circle to malfunction. There were US radars to detect incoming Soviet aircraft. This was the height of the Cold War, remember? Well, some of you probably are too young to remember the Cold War. But the first thought was it's the Soviets jamming the radar because they're going to attack. Fighters were scrambled. It took a while. And the Soviets too thought, because their radars too were misbehaving, that the Americans are going to attack. Fortunately, the US Air Force already had solar observatories because they had realized that the sun could affect this, and things calmed down within a few hours, but it could have happened. So it's not just, simple technology. It could have had, think of a third world war with nuclear weapons. So it could have had a society, a civilization ending effect. So let me get a bit into the science. Talked about the sun being a magnetic object. So this is an image of the sun, a part of the sun. You see these dark spots. These are areas of strong magnetic fields. This is what you would see if you were able to look at the sun, well, through a filter. However, these dark spots are not necessarily dark in all other wavelengths. If you were able to see UV, the same dark spot would appear bright. So let me explain what these are. These are a series of images taken within solar images, taken within seconds of each other through different filters. That's a magnetic image. This is what you would sort of see if you would see it through your eye. This is, this is H alpha, so slightly lower wavelength, slightly redder light. And these are basically ultraviolet images. This dark spot is this bright patch. It has enormous amounts of energy. What we see when we normally see the sun, and Galileo is the first recorded person to observe it, are these spots, which we call sunspots. Very imaginative. But thing is, sunspots appear cyclically. The number of sunspots increase, decrease, increase, decrease, increase, decrease. The ones labeled in blue are the so-called modern sunspots, and we've started numbering them from here. So we are currently in sunspot cycle 25. So it is at close to the sunspot maxima that these emissions and flares and everything increase in strength, because that's where you have the most sunspots, which are the most highly concentrated magnetic regions. So the sunspot cycle, this is just a pretty picture of sunspot cycles from the sun from 1997 to 2017, okay? You can see the sun, this is an extreme UV image. You can see the sun being very dim to suddenly becoming very bright. And a better image, because it's not moving, oops, is this. You can see that in let's start, 96, it was dim. That's the minimum. We call it the solar minimum. It started getting brighter and brighter and brighter and brighter till it became very bright. This is solar maximum. Then it started going down, 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 down till we hit solar minimum again. Up, 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 up till we hit solar maximum again. Down, 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 minimum again. We had just crossed the next maximum. Okay, so it's a cyclical event. Now, these sunspots don't appear at random. So this is an image showing sunspots. Starting, it's a fairly long. So at the beginning of the cycle, of a new cycle, sunspot appears at high latitudes. And as the the cycle continues, it keeps occurring at lower and lower latitudes. So for obvious reasons, so this is the northern hemisphere of the sun, this is the southern hemisphere of the sun. So for obvious reasons, we call it the butterfly diagram. So any theory that wants to explain solar magnetic fields has to explain this. This is the first set of observations you need to explain. But this is just a nice, pretty picture to show. A less interesting picture, for most people, but not to astrophysicists, is the same picture, but in terms of the magnetic field, the actual magnetic fields of the sun. So you can see that not only is the magnetic field decreasing at solar minimum, but the North Pole and the South Pole reverses. See, yellow and blue are different magnetic fields. So at the North Pole of the sun, blue becomes yellow, becomes blue, becomes yellow. So the sunspot cycle is roughly 11 years, but this magnetic cycle, which we call a Hale cycle, is 22 years. Now, this is another thing. You have to explain the reversal of polarity if you want to explain this. So the question is, what is the big problem? Why can't we do anything? We can't predict these events yet. Now, you saw in this figure that the magnetic fields have different strengths. Some are very strong, some are not very strong. So forget about predicting the events. We can't even predict the strength of the next cycle properly. There was, in fact, before this solar cycle 2024, NASA had asked lots of people, each of these color bars is a group of researchers, to predict the strength of cycle 24. This is the range of predictions. It's all over the place. This was the actual value, the actual level of the cycle. Now, we had the same thing for cycle 25, except you'll find that fewer people were willing to do it after the last time. We are still waiting for the final results. Yes, we have gone through one maximum, but often the maxima have double peaked, so we have to wait to see if there's a second peak. So I think we'll need another 2 years before we know which of these results is correct. So we're waiting. But as I said, we are hopeless. Now, this is where I'd like to talk a bit about my science. What is my approach? I look for changes deep inside the sun, not at the surface, because the magnetic fields have to come from deep inside the sun, and check, is there a way to predict them? Okay, because I'd rather go to the root of the problem. And what do I do with this with? I use helioseismology, which is studying the sun using seismic data. Geophysicists study the structure of the Earth with earthquakes. Fortunately for us, the Earth doesn't quake all the time, but the sun, being a fluid, quakes all the time. And I use that data to figure out what is happening deep inside the sun, both in terms of structure as well as in terms of dynamics, meaning rotation. So what have we seen? Now, before that, a pretty picture. So what do solar oscillations look like? That's solar oscillation. Sorry, it's a bit glitchy because of the not showing it directly. Now, these are actually sound waves. So if you know a bit of physics, you'll say, how do we observe sound waves through the near vacuum of the interplanetary medium? We don't listen to the sound, we look at its effects. It's like, think of this. If you have a drum being played and you are somewhere outside, I get the cursor out of the way, you can see, if you had good vision or a good microscope, the small deformations of the surface of the drum because somebody is hitting it. That's what we observe. And then resolve that into the different types of quakes. Okay? And the reason we can study the entire sun deep inside is different quakes go to different layers of the sun. So these are called modes. It's like notes of a musical instrument. Some notes have high pitch, some notes have low pitch. It's exactly like that. Okay, so you have the fundamental and its harmonics. If you play a musical instrument, you know that how to change pitch and what, if you change, say, the material of the wire of your sitar, it's going to give you a different type of sound. That's exactly what we do. We analyze this and figure out what the sun is made of, how it rotates. The details are technical, but actually the science is not very difficult. Now we expect the sun, theory says, to look like this. There's a core where nuclear burning occurs. About 70% of it is a basically inert layer where heat is transported by radiation, photons, the matter doesn't move much. And the outer 30%, theory says, is boiling, churning. So what do we actually see? Oh, by the way, when helioseismology just about came up, Gary Larson, some of you may be fans of the far side, said, maybe this is what's inside the sun. There's somebody who pulls a lever and says sunrise, sunset. Now, this would be really interesting. But the structure of a star is really not very interesting. It's very simple, which is a good thing for stellar astrophysicists because we can actually study them because of that. This would be almost impossible to study. Now, what have we found with seismology? Indeed, the inner 70% is placid, and the outer 30%, actually not quite 30%, we know the number to precise precision, is a boiling, churning mass of plasma. Do we know this is correct? Well, yeah, because we can image the outer layers of the sun, and this is what it looks. Let's see if this movie plays. Not very well, but it hopefully will play. Sorry. Movies, here. Movies are not cooperating with me too much. But you can see the movement. This is an actual image of the surface of the sun. So you can see these motions. So we know we are right. Okay? It turns out that the structure of the sun is exactly what we expect it to be, with the temperature in the core of the sun a whopping 15 million degrees. Our models actually reproduce this very well. Okay? More astounding is the density of the solar core. Now, 1 cubic meter of material at the center of the sun weighs 150 kg. Now, we consider lead to be very, very dense. That's only 11.5 kilograms, not much. So we're talking about really dense, really hot regions, but theory agrees with this. So where does solar cycle come in? For that, we need to look at rotation. The fact that sun rotates was discovered because of the sunspots. Galileo discovered sunspots. There was a Jesuit priest named Christoph Scheiner who was hell-bent that the sunspots are merely atmospheric clouds because the sun can't have defects. So you can't have a heavenly body with, things like spots. So he kept meticulous pinhole camera records of sunspots. He couldn't prove anything, but his observations showed that the sun rotates. His observations also showed that the sun is at a slight angle to us. We all have learned in school that the Earth's axis is at an angle of 23.5 degrees. Well, the sun's axis is at an angle of 7 degrees. These meticulous observations can tell you that. Okay. Now, so we've known that the sun rotates. Of course, modern observations have shown that the sun rotates. This is a movie seen from the Soho spacecraft. You can see the sunspots rotate. You can find the rotation rate. It turns out the sun doesn't rotate like a solid body, not like the Earth. A day in the solar poles is 32 Earth days. A day at the solar equator is only 25 days. Okay, now this means if you had a magnetic field, you could wind it. That is probably what happens. Most dynamo theories think, and if you wind a magnetic field, you strengthen it. Okay. What about the interior of the sun? Okay, so this is a cut of the sun. This is the surface. This is to the interior. Now, the color scale is shown here in units that only helioseismologists use, but so I've translated it in days. So this is the translation of the color scale. So red is fast rotation, blue is slow. And what we can see is that the surface rotation rate continues up to this point, which roughly continues up to that point, which I've marked by the dash. And that is where the churning ends in structure. And then it becomes like the Earth, meaning a solid body. Why do I show you this? Because this picture changes, except that the changes are small. At the equator, the sun rotates with a speed of 2 kilometers per second. The changes in the rotation rate are about 10 to 15 meters per second. Very difficult to detect. How would I detect here? If I drew another picture like this, it would look exactly the same. So what we do is we make pictures at different periods of time, so say 1996-7, and from each we subtract the average over time. So that'll give us the tiny signals. So this scale is now minus 10 to 10 meters per second. So you can see there's a change. This doesn't look like much because this is not a good representation. What we do is take the rate at any given radius and plot it as a function of time and latitude. That is interesting because this is what you get. The red bands are faster than average rotation. The green bands are slower than average rotation. But if you plot, now this shows 2 different solar cycles, okay? And in each, if you plot the position of the sunspots on top of this, they fall bang on this faster than average rotation, which means there's a direct physical correlation, we don't yet know what, between the emergence of sunspot and this layer, this moving layer. We still haven't figured out the physics, but using this, you can actually see that this solar cycle began in the middle of the previous solar cycle. So we should be able to predict the next solar cycle from this, if we understand a bit more of the physics. Now, what about the solar events? Because this is, a bit global. For that, we think we do the same thing, but look at tiny patches of the sun. And what we are finding is it's not these velocities, the velocity of the flow on the sun that matches these colored regions are strong magnetic fields. The arrows just show the velocity. And you can see this is a bit jumbled. But if instead of using the velocity, we use the rate at which the velocity changes with depth, that has a much better correlation with these magnetic fields. So we are going to see if we can use these data to figure out where these magnetic fields will emerge. I've just managed to get some NASA money to do that, but it's a few years of work. So before I leave, I would like to leave you with a few things, a few take-home points. One is we understand the internal structure of the sun, but the outer layers where we have these sunspots, that's still a bigger problem. We don't know that. We do not completely understand the changing magnetic fields. There is no coherent theory yet of solar dynamo. There are multiple theories which can explain certain parts of the observation, but nothing that does a global job. It's a hard problem. We are not yet able to predict the strengths of the solar cycle, so consequently, we cannot yet predict the potentially harmful events. But there is a huge thrust of work done both in Europe and in the US. Not sure in India how much that's done, though there is some work being done to see what we can do to predict space weather. We all know how difficult weather prediction is on the Earth. Can you imagine trying to predict space weather? So it is a tough problem. So thank you very much for your attention. I'll be happy to take a few questions if you have any.
Hi, yes.
Hello? Yeah. Here. It was a nice lecture, something new we learned today. I have a couple of questions. First is Voyager 1 and Voyager 2 have already left the solar system. They are out of the solar system now. Now they are, both of the devices are solar powered. So how?
No. Voyager 1 and Voyager 2 both have nuclear reactors.
Okay.
They're not solar powered. And that's also been a part of the problem because there was this huge backlash about having nuclear reactors on a satellite, because if the launch vehicle fails, it'll fall on Earth and contaminate. So they have nuclear reactors on long arms with small nuclear reactors.
But then how much is the life of these devices? How far they can go?
That is not known. It's not a question of how far they can go. They can actually go very far. They don't need much power to go. It's a question of how quickly can we communicate with them. Right now, it takes more than 23 hours to send a signal there, and another 23 and a half to get back to, more than 23 to get back to us. That's the problem.
Okay, now related to this question, I mean, on Facebook, I keep getting these messages that Voyager 1 is about to reach 1 solar day distance away from Earth in a couple of months. Maybe in 2026 that will happen sometime after August. Now, considering this fact that it took almost 45, 46 years to reach one solar day distance, can we even imagine that mankind will live that much to cover a distance of one light year?
Probably not, but you have to remember this is old technology also. These satellites were built and launched in the 1970s.
Okay. Because it runs on 64 kilobytes of memory, which is very small as compared to today's.
That's what computers were like those days. You forget how quickly computer technology improved. When I did my PhD 30 years ago, I did it on a computer with a memory RAM of 64 kilobytes. Your phone has more RAM than that.
Okay. And a different question. Whatever we saw just now, sun is a very violent device, a very violent
It's not a
star.
very violent star. It's actually a very benign star. If you want to go to a violent star, go to Proxima Centauri.
Okay.
You remember there was this huge hue and cry when people found a planet, a rocky planet around Proxima Centauri, and said, "Oh, it's our closest planet, so maybe we can do Earth. We can go there." It's around an M dwarf, which is highly active.
Okay. Understood. And is there any possibility to find a new element such that the present periodic table will get upgraded with a new element because of this research on sun?
No.
Thank you.
There's a question here. Okay. And
How-
there's one here in front also.
How do we seismology? You said something about seismology, solar seismology. How that impact is made on Earth? We
don't see the impact on Earth. We look for tiny changes on the surface of the sun. Do you know what Doppler effect is? Doppler effect is when you have a wave, you're moving away from the wave, or the wave is moving away from you, it's low frequency. And if it's towards you, it's high frequency. We take Doppler images of the sun because light also undergoes Doppler event. I might actually have a slide. Yeah, I do have a slide. Oops. Yes. So this is a Doppler image of the sun. What you're seeing here is basically rotation. This limb is going away from you. This is coming towards you. Okay. You get rid of the rotation signal. We know how to do that because we know the rotation very well, because this is all at the surface. This is what it looks like. Most of this motion is because of the churning gas at the surface of the sun. So we get rid of this by averaging over 45 minutes to an hour. And this is the signature of the oscillation. This is the sun quaking. Here's a movie. We see images in light. We don't see the sound. And this is so small. The change in the brightness of the sun because of these is a part in 10 to the 6. That is a part in a million. So no, it has no effect on Earth. Fortunately.
Ma'am, thank a solar flare, we thanks the Earth magnetic field and thank SSA damages our atmosphere.
Could you repeat that, please?
Ma'am, a solar flare or solar event. Thank we thank our Earth, our magnetic field. So thank it damages ocean air or Earth's atmosphere.
It could. Fortunately, the sun is not that powerful. So the damage is going to be minimal. There, as I said, if you go to the planet around Proxima Centauri, there people have done calculations of what would be effect of the atmosphere. The flares could be powerful enough to even ablate the atmosphere completely, to get rid of the atmosphere. The sun is actually quite benign. It's all the fault of technology.
Yeah, ma'am. So you said the sun has two different rotations. One is at the poles and the equator.
No, it's a continuous change.
Oh, how did we found out that it has differential
Sunspots.
rotation?
Sunspots and other mechanisms like that. Yeah, it's a easily observable thing, at least on the surface. Yeah. There's a question here.
Sorry, thank you for the talk. I was also wondering, you mentioned how when the particles from the sun come, the magnetic field of the Earth on one side gets compressed and on the other side gets extended. I didn't totally understand like how that works.
Because charged particles affect magnetic fields. So it's basically you're putting a pressure on one side, and what happens is the wind is flowing past it, and the wind has magnetic fields, so it just carries the magnetic field along the other side and opens the tail.
Okay, thank you.
Ma'am, first of all, good morning. I want to ask, I have two questions about regarding this. First is about the Parker Solar Probe, which gets to the sun. So can we have such a data that of from that satellite that we can able to know more about suns? And my second question is that do we know that if suns fuels get over, does it becomes a black hole or a neutron star?
Okay. So the first question is, yes, the Parker Solar Probe was sent so that we can figure out the fine details of what the magnetism of the sun does close to the sun. Okay, so it's within the sun's corona. So yeah, that's why we say it's touched the sun. It's actually nowhere near the photosphere, but it's in the sun's corona. But you see a lot of the images there. As to your question, what will happen to the sun when hydrogen is depleted? It'll start expanding. It'll first become what we call a subgiant and then a giant. And in the giant phase, it'll swallow us. Okay. And then it'll become smaller again. But then what will happen, because then it'll become smaller because it'll start fusing helium in the core to become carbon. Now, the sun doesn't have enough mass so that once helium becomes carbon to fuse carbon. So what's going to happen is, because there's no source of energy, gravity is going to contract the sun's core, but it won't be able to contract it too much, so the sun will die as a white dwarf. It'll not become a neutron star, and it'll definitely not become a black hole. It'll be a white dwarf.
And one last question is that why does, as what I said, that why does this take the charged particles, photons, millions of years to get out of the corona of the suns to the
No, from the corona of the sun, it doesn't take millions of years. The corona is very thin. It takes millions of years to get from the core to the surface. And that's because the place is so dense and so opaque, the photons can't just come out. They go there and get hit by another particle, and they do this. It's like a drunk man walking. We call it a random motion, a random walk. So that's why it takes so long.
Thank you.
Thank you for the talk. It's such an amazing talk. My question is, in such solar events like a solar flare or a solar storm, is there any way for us to prepare for it? That is, in power outages and such things.
In principle, yes. In practice, none of the power companies are willing to spend the money because these are low probability, high impact events. The probability is low, so why spend the money? All you need to do is have a few trigger switches to switch them off, but then you have to do the monitoring to know when to do the trigger switches. So I've been talking to people who are sort of related to the power company, the electrical grid company, and they said, oh, why? It's a 1 in a 10,000 probability. Why bother? So that's the problem.
One more question. We visualize magnetic fields as field lines.
Yeah, which is what I had drawn there because that's a field line.
So when, say, the sun or the earth moves, does it take that one specific field line with it, or does it create a new one?
No, it takes it with it.
Okay.
It's like moving a magnet. You've played with magnets in school, right? You take the magnet and move it there, it takes the field lines with it. You're just moving the magnet. Okay.
Hello, ma'am. Good evening.
Sorry, could you raise your hands? I don't know who's speaking. Okay.
My question is somewhat philosophical, I would say. Like, I want to ask is that humanity hasn't understood our own planet yet. We have many questions unsolved. Then, how worthy is it to study the things which are millions of light year away from us? Then those we have many problems yet to solve here, and we are facing many, like climate change or many other things are here too.
You have to spread your resources to gain knowledge. I mean, you could say things about the Earth too. Why do you bother to study what's happening at the Earth's core when there's so much problems on the surface? Okay. You have to gain the knowledge, and to do that is let the people who are interested in doing that do that, and let the people who are interested in solving problems on the Earth do it. Because the only way you make advancement, look at the advancement of science through the ages. Yeah. It's not, you can't not study something. If there are people interested enough in something, they will study it. And if you want to increase the amount of knowledge humans have, you shouldn't be restricting that.
Okay. But is it like that? Means the study which is
I think we're sort of out of time now. It's time to head out to get some tea and snacks. Please, Professor Basu will be around, so please, if you had any questions, please do.
Yeah, I'll be happy to answer with a cup of tea.
Yes. Yes. All right. Thank you so much once again to Professor Basu. It's been a great privilege to have her, and we'll see you outside for some tea and snacks.
You've had some excellent questions, so thank you.